Okay, so let's start with the peptide bond formation. It's formed by this carboxyl and this amide. So the hydrogens on this nitrogen are lost, and then the hydroxyl group is lost, and then they form our peptide bond. So since the carbonyl-carbon is connected to two very polar atoms, there will be renaissance and lack of rotation, which means restricted possibilities for protein folding. As we see on the alpha carbons, they each have an R group. Essentially, we'd want them to be in the trans position because it's more stable, but these R groups will determine the phi and psi angles along with the final folding. Moving on to our phi and psi angles. So our phi angle will be on the nitrogen side before the alpha carbon, and the psi angle will be on the carbon side after the alpha carbon. So I have them labeled with different colors, where this dark one is the peptide bond, and there again will be no rotation along this, but there will be along the phi and psi angles. So moving on to our alpha helix. So it's a right-handed alpha helix, and there is a hydrogen bond between every fourth amino acid. And in this, the R groups are sticking out, and the phi and psi angles for this guy would be -60 and -60. Moving on to our beta strand. It's an extended one, so our groups are sticking up and down, and the anti-parallel version of this is more stable because the hydrogen bonds are stronger, and if we add another strand, it becomes a sheet. For our beta term, we again have that hydrogen bond going on. It's a full 180 reversal, and the proline in this can form kinks and sharp turns, and the glycine allows it to be flexible.